positive or negative, we will be in a position to predict whether the reaction is spontaneous or non-spontaneous, spontaneous, non-spontaneous. So we plug in this equation and make a conclusion whether the reaction is spontaneous or non-spontaneous. Point to remember before we looked at example here is, this is always given in kilojoules per mole, kilojoules per mole. This one is in kilojoules per what? Kilojoules per mole. And this term right here, not the temperature, but what I'm circling right here is always given in joules per mole. So wherever you plug in this equation right here, you need to change this term here into kilojoules so that everything will be in kilojoules. Everything is in kilojoules. For example, there's an example given here. If you look at the thermodynamic terms here, this is in kilojoules. We cannot ignore this. We cannot ignore this. Look at the units, joules per mole. This is in kilojoules per mole, and this one is in kilojoules per mole. So for this to be in kilojoules, we need to change that to kilojoules. And of course, you know, 1 kilojoules equals to 1,000 joules. 1,000 joules. Change that. And you plug in the what? In this equation and make a conclusion whether it is spontaneous or non-spontaneous. Spontaneous or non-spontaneous. There is one thing I need to, point to you, or you may have read in the background. When we have this superscript note here, it means at standard state. If I have superscript note that is at standard state, this is at standard state, and this is at standard state. Standard state means the pressure equals to pressure equals 1.000 atm atmospheric, and concentration or molarity should be 1.0 molar, and temperature should be 298.15 Kelvin. If we set the parameters to these units here, and then we are working at standard state. If there is a way we can adjust the, the lab pressure to be 1.00 atmospheric pressure or 760 millimeter mercury, and we have a solution whose concentration is 1 molar, and set the temperature to 298.15, we say that the condition is at standard state. So if we are working with standard state, this means you should know what that means. The temperature should be 298, all right? And these terms right here, they are the literature. In the text, we are given the literature values for different compounds. If you look at the Abedex or in any general chem text, you should be able to see thermodynamic terms, and you cannot miss to see this enthalpy of formation and entropy and free Gibbs energy for formation for compounds. Now, from this equation, we can calculate each one of them. For example, let me just show you how you can calculate change in free Gibbs energy at standard state for formation. For that is given by the summation of, we need to have a bracket, that is M, for products minus summation of N reactants. This stand for, all right, I shall have summation of G. This should be G naught, and this should be G naught for the reactant, product minus reagent. Basically, this is for what? Products minus reagents. The M and N stand for the coefficient in the balanced equation. In the balanced equation, for example, if I was to calculate for this chemical equation, the coefficient is 1 to 1 to 1 to 1 to 1. If it was something else, and then we have to plug in the coefficient in the balanced equation to calculate the G no, that is at standard state. If it is at standard state, you got to refer to the thermodynamic terms, or sometimes you'll be given. For enthalpy of standard enthalpy of formation, we do the same thing. That means formation of M, that is H for product, minus enthalpy. This is summation for N, that is the coefficient in the balanced equation, H for the reactants, and we get ourselves, this is a standard state, this is a standard state product, that one is a standard state. You do the same thing for what? You do the same thing for entropy of formation, delta S superscript naught, given by the summation of M coefficient in the balanced equation, S naught for product minus summation of N as for the reactants. These are equation not covered, maybe partially covered in the lab manual, but should be covered in the lecture. I don't want to, go in details. If you look at this equation right here, if I look at this equation, to find the enthalpy of formation from this chemical equation, product is nitrate and ammonia. Nitrate is enthalpy of formation of nitrate and ammonia. You see ammonia, nitrate, you add them together, this is the product. Pay attention to the sign, minus, in parentheses, product. We have only reagent here, so we subtract and it is positive, positive 6.40 for this particular reaction. And from the thermochemistry that positive value means endothermic, or enthalpy of change in enthalpy of formation for a positive value, endothermic, negative, exothermic. You'll do the same thing for entropy of formation. You're gonna do the same thing for entropy of formation. The S gonna use these values. However, this is in joules. You got to change to kilojoules. So that you have that, and then you plug in the equation. If you look at all these are standard state, and if we plug in this equation, ending up with a negative value, the way it is written in this equation, we can say that placing ammonium nitrate in H2O will spontaneously dissolve into respective ion. Remember aqueous and aqueous, it will spontaneously dissolve. Suppose we flip the equation and we do the same thing. Will the reaction be spontaneous, or in other words, will ammonium nitrate, which is solid, spontaneously be formed from these two ions? If you plug in the same equation, you will realize that it will be positive and it's not going to spontaneously form the solid. So all the chemical reaction you look at is the opposite of KSP. Remember, for KSP, such as for silver chloride. Give you an example on what is going on. This one doesn't want to go to what? To solution. Lies towards the right to produce silver ion plus chloride ion. This is aqueous. This is what we looked at in solubility. But today, in today's experiment, precipitation, we are asking ourselves, suppose we get a source of silver ion, all right, aqueous, plus, all right, plus chloride ion. Will the solution produce silver chloride solid? Silver chloride solid. That is the question we're gonna find out from calculation. From the calculation, we should use those terms or the numerical value from delta G to determine whether the reaction will spontaneously form the solid. Remember, if we are to write the KSP for this, let's see, if we are to write the KSP for this, remember it is product over what? Product over reagent, product over reagent. And when it is solid, it's assumed to be 1, and it's just gonna be 1 over concentration of silver ion times concentration of chloride ion times concentration of chloride ion. Product over reagent. This is solid and it's understood to be only 1. Only 1. Suppose we have something else such as calcium chloride. So we have calcium. Calcium, which is aqueous, plus hydroxide, aqueous, all right, hydroxide, which is aqueous, and the product, will it form calcium hydroxide? We have 2 here. Will it form calcium hydroxide? The key thing is you should balance the equation. This is calcium hydroxide. For KSP for this, is a product over reagent, 1 over concentration of calcium times concentration of hydroxide square, concentration of hydroxide square, product over reagent, product over reagent. So we have to predict whether this will form a precipitate or not. There is a way. Remember, this is not at standard state. We are not going to use the equation given here to determine whether the reaction will be spontaneous or non-spontaneous. Why? Because in the lab, the room pressure is not 1 atmosphere. You will be working with, or assuming that if you are to come to lab, you are going to use a different concentration. These are in the procedure. Look at the procedure right here. Can you see the procedure? Can you see the procedure, please? Are we together?
Yes.
All right. If you look at the procedure, we are, it calls for using 0.2 molar. And of course, the room pressure is not 1 atmosphere. So we have to use a different equation to complete the data sheet. And I'll walk you through that. We will be finding this, not delta G naught. We will be finding delta G. Maybe I should use a different color and bring my iPad. Where is my iPad? Right there. This is the equation you will now use to complete the data sheet. It is a delta G, not naught, but reaction. This is at non-standard state, equals to delta G naught delta G node formation, which we used the previous equation, plus R T, and this should be in Kelvin. This should be in Kelvin times natural log of ln of Q. This is the reaction question you looked at before. This is the same as, you know, concentration of the product over concentration of the reagent, the way I've been doing before, reactants. And this is temperature, and we're gonna be using, everybody will be using this, value. We'll be using 298.15. Everybody will use this. This is what we're gonna be using for our calculation. It's going to be that 25 degrees Celsius. And this one, we use the equation I gave you before, and this is delta G naught, all right, formation is given by delta H formation for that. This is subscript formation minus delta, that is temperature. And remember, we are using 298. We're using 298 times change in entropy superscript. These are thermodynamic terms which we'll have to employ the, we're gonna use the, we will use the values given in the lab manual. All right, these are the values we'll be using to find delta G naught. It's already given for each one of us to find the S, product of reagent, or say that is delta G naught formation is given by change in delta G naught for product. Should be product, this should be product. Let me just erase that. Summation, we should use summation for this. This is the equation. For that two equation we use here, summation of delta G naught. This is not product, and there is M for the coefficient in the balanced equation, minus summation of N, delta G naught reactant, delta G naught reactant right here, R for reagents. Forget about that, we use this one right here. This is the equation we will use. This, what is in the bracket? Can you see what is in bracket, what I have in parentheses right here? Somebody's out there, can you see this equation?
Yes.
The equation in the box, as my iPad is blocking, but nevertheless, the product you will need to use, let me take that aside. If you look at this equation, this is what you will use in product minus reagent to get that. Forget about this. This might, we don't have that. Where are we getting all these values? And that is why we have this thermodynamic on what? On table 1. Table 1, we will use to find this term. Look at my iPad. This term right here, we get from here. And on the screen, can you see on the screen the table 1? Are you able to see the screen on table 1? Can you see my screen? Somebody say yes, Aliyah. All right, thank you.
Yes.
Yes. This is where you will get the values to plug it in this equation. R here is 8.0 314, and this is in joules. So the term right here should be in, remember, this will be in kilojoules. This part right here will be in kilojoules, but this term right here will be in joules because of the R value. R value make this term to be joules and this term to be in kilojoules. So if I were you, I'll do here, assuming that, you know, it is in joules and then divided by 1,000 to change to kilojoules, and then you add everything and see if you end up with, you know, if you end up with a negative value or positive value. If I end up with a negative value or positive value. Remember, this term right here is at non-standard state because that is the condition in the lab. We assume that now you are in the lab. This term here, you're gonna use this table to find out. I've given you the R constant. It's not 0.08, whatever you are used to forecast constant. This is energy, and energy should be in joules. Should be in joules. That is the value you need to use. Joules per mole. Joules per mole, like that. Joules per mole. Now, let me go back to the equation. We're almost getting there. So you know the temperature. See the temperature. This is the temperature you're gonna be using. What is hard now is how will we find the reaction quotient? Reaction quotient. How will you find out this term right here? ln is a function on your calculator, but how will we find this reaction quotient? How will we find out that? All right. How will we find out that? It is by, all right. It is by looking at the reagents. Before I walk you through this one right here, this term right here, let's go back to the procedure. I will pull the procedure so that we see how to find the natural log of reaction quotient. If you read the procedure here, 0.2, we know the concentration. All reagent for this particular lab, the concentration is 0.20 molar. All right. And for 0.02 molar, you are mixing equal amount, things called for 4 drops. Look at right here. You're gonna take 4 drops and add 4 drops. So 4 and 4 makes 8. The volume will, we assume that the concentration, number of moles, a function of number of moles. If you double the volume, the concentration will reduce by 1/2. Reduce by 1/2. Maybe using an example, you will see how the concentration changes when you mix two reagents. Bear in mind that you have this concentration for all the reagents on the data sheet, and you are mixing equal amount, whether it is 4 drops, whether it is 10 drops, 10 drops of each reagent, 10 drops of each reagent. And if I look at, if you look at I don't think there is see here, this equation right here. This equation right here, before we look at one example on the data sheet, on my iPad, look at on my iPad, assuming you have barium nitrate and calcium what? And calcium, barium nitrate and calcium iodide. Which one will be our precipitate? It is double replacement reaction. So let me draw some diagram right here. I have 0.2 0 molar barium nitrate. you got to write the correct formula for your reagents. Nitrate shouldn't be 3. This is what I meant to say. Oh, it's not responding. Mine is not responding. So I put that. Barium nitrate is PaNO3, 2 like that, on 2 substrate, and I have my calcium nitrate. Here is calcium iodide, not nitrate, iodide, and this is aqueous. Let's just assume that aqueous. You have 2 reagents. The concentration here is 0.20 molar. We are mixing equal amount. You see smaller right there? We are mixing 2 reagents. So I have 2 beakers right there. You assume that this is a double replacement reaction. In double replacement reaction, assume now the reaction mixture have these ions in the solution. Barium is positive 2, and nitrate, I'm just generating ions from the first reagent. From the second reagent, I have calcium and I have iodide, like that. She'll have knowledge on, the ions. Is it positive or negative? By looking at the chemical formula, you should be able to predict the ions. So if it is double replacement reaction, we are saying that if this one is combining with that, is it going to form a solid? We are predicting whether it will form a solid. Will this one form a solid? So we assume each one of them is forming a solid. We assume each one is forming a solid. And with that, if the products, look at the products, when you exchange the ions, we are saying that is barium ion going to form like that, aqueous with iodide, all right, aqueous form barium. You force it as if it is solid. We don't know which one is solid. This is barium what? Iodide. And the second reagent, all right, second reagent is, or second reaction. So we assume that there is another precipitate, there is another possible precipitate here, calcium and nitrate, like that. All right, calcium nitrate, this is negative aqueous. Will this one form solid? Will this one be a solid? Calcium nitrate. So each one of them is a possible precipitate. Each one is a possible precipitate. So I make this one solid. There's a 2 there, and then make that solid, and then make this solid. So at the outset, once you do the double replacement reaction, once you switch the ions from your reagents, you assume each one of them is a precipitate. And that is why, let me talk to, before I showed you the concentration, let's see the data sheet. Here is the data sheet. If you look at the ions, this is from the first reagent. I'll come back to this example again, and there are 2 possible precipitate. We don't know what it is. We just did double replacement right here, and we say this is a possible precipitate, this is a possible precipitate. These 2 right here is, all right, delta G naught. You use this to find this column for precipitate number 1, precipitate number 2. You use this equation. Look at my iPad. You should have this equation right here. This is the equation you will use to find right here. at the bottom right here, this is what you will need to find for precipitate number 1, precipitate number 2. And then find now the non-standard state using this equation at the top right here. We're gonna come back to that. Where I'm walking you is this reaction quotient, So if I have, let's fast forward to where we were. This is where we were, all right? And remember the concentration was what? The concentration was 0.2, 0.2. What I'll do is look at the ions from the initial reagent. This is what you had when you look at the mole ratio. This is just by itself. We haven't mixed it. So here is the concentration of barium ion. And remember, for nitrate, it is twice the initial concentration, which was 0.2, because mole ratio is 1 to 2. 1 to 2. So you multiply by 2 what? You multiply by 2 the concentration of nitrate. You do the same thing for calcium. It was 0.2 calcium iodide, all right? 0.2 molar calcium iodide. So for calcium, it is 0.2 molar because 1 to 1. But for iodide, it is 1 to 2. 1 to 2. You're breaking down into ion. The key thing here, you got to balance the equation. When you split the ions, it's 1 to 2. It's the way you write KSP, or the solubility equilibria. Solubility equilibria. And then you write the concentration at the top. Here we have not, in this equation, we have not mixed the, all right? We have not mixed the solution. We have not mixed the solution. Now, in my iPad here, once I mix the solution here, this is now mixing that they exchange the ion. If you look at the iodide, it has combined with barium. Nitrate has combined with calcium. When you mix the solution, the two solutions, the concentration will be half what you had initially for each ion. When you mix the two, so assume now all these they are in one beaker. They are in one beaker. The concentration will be a half of what you had before. So this one will be 0.1. This will be 0.1 molar, because it is 1/2 of what I had before I mixed. What will be the concentration of nitrate? Before I mix, it was 0.2. So it's gonna be 0.20. Half of what I had initially before I mix. I've mixed everything. For calcium, it is 0.10, half of what I had. For iodide, it is 0.2, 0.1. It's 0.1, not 0.2, not 0.1, 0.2. Let me take a pause right here, and ask a question. Are we all on the same page on how to find the concentration after when you mix the two? What I have on the PowerPoint slide on my iPad right here is after mixing the two solution, that is the barium nitrate and calcium iodide. Before I mix, you should come up with this cartoon right here. Otherwise, you may get frustrated not knowing how to move forward, Are we together? Anybody? Let me see. Did anybody ask a question? Question? By the way, there's somewhere you can raise your hand on the chat room. You can raise your hand if you want to. If you have a question. Do you have any question on how to find the concentration, first of all? Any question? Can you hear me? Aliyah? Amy? Oh, everybody's muted. Let me see. No question. I have no question. All right. All right. So this is now what I need you to understand, how to generate or how to arrive at this concentration, that it's going to be 1/2 of what you started with. And remember to multiply by 2, you got to write the solubility factor. You assume it is a solid. And this is what you have. Now, if this is what my solid is, barium iodide, reaction quotient, you know, Q, if I write Q for the first reagent right here, Q will be product over reagent. Product is 1. When you have solid, don't just get confused on where the solid is on the background right here. Use what I have here, that solid product over reagent. And by the way, I forget to balance the equation. Sorry about that. For the first reaction, there should be a 2 there. To balance the equation. For this, there should be a 2 there to balance the equation. So that for the first reaction, make sure you balance the equation. For the first reaction, it will be concentration of the reagent, which is for solids, it is 1. So always 1 will be at the top. Let me give you a hint. This your way is to know that 1 will be at the top, and then your denominator will be a function of your concentration once you figure it out that. So if I look for barium, it is 0.1 raised to 1, because the coefficient is 1 for barium here. The coefficient is 1 for barium. And for iodide, it is 1 over what? 1 over, it is 0. This is 0.1 raised to 2. This is raised to 2. This is my reaction quotient. Whatever I'll get here will be my Q, and I'm trying to find my calculator. I don't know, I have a lot of papers here. I had my calculator earlier on. I forget my calculator somewhere. Can't find my calculator. But you know how to plug in. Oh yeah, I got it. It's right here. Got my calculator. So if I want to find, it's gonna be 0.1 square, all right, for iodide, times 0.1, and then the inverse of that, I get it is 1,000, and then you find ln over 1,000. So if I go back now, this is the same as 1,000. You go back to your original equation. Let me see if I can go back. This equation here, you say ln over 1,000, ln over 1,000 there, ln over 1,000. So ln over 1,000, what is ln over 1,000? I get 6. And you'll say times now whatever temperature you have times, you know. And remember, this part right here will be in, this term right here will be in joules. So we will have to divide by 1,000 once we are done, multiplying with the values. And then we plug in there and see if we end up with a positive. Remember our, what I said earlier on at the beginning, that the conclusion is, if it is negative, we say it is spontaneous, it will spontaneously precipitate, all right? Spontaneous, non-spontaneous. You see here, for a negative value, you say it will spontaneously precipitate. For a positive value, you say it will not precipitate. It will not precipitate. So in your reaction for each experiment, there is no way you will end up with both being positive, being negative. You'll not say this one will precipitate, this one will precipitate. You may end up with a situation where there is no precipitate. It's fine. You use the equation and that's what the values tells you. For example, if I do, all right, if I plug in in my equations in the illustration I use here, and end up with positive and positive, positive and positive for that, and then I'll say, oh, it is, no precipitate, no PPT. If there is a PPT, they expect you, or I expect you to write the chemical formula. In here, look at here, precipitate, write the chemical formula for the precipitate. Right here, you're gonna write the chemical formula for precipitate. If there is no precipitate, that means positive, positive, you write NR. NR for for no precipitate. Let me just minimize this. I think I can minimize and then we go back and see. So I don't want to just create, that's how you find the ln of Q, this term right here, and you said there'll be calculation. Now, I will, or somebody pick for us, for the entire class, which reaction do you want me to use as an example of the data sheet you have? And I hope you are able to fix. Let me see if I use the correct one. There was a mistake before in the previous data sheet. It was sodium nitrate and calcium nitrate. That was wrong. And this silver sulfate, it didn't have subscript 2, so take note of that. I want somebody to volunteer and tell me which example do I use to show you how to complete the data sheet. And this is due next week. Which one do you want me to use on the data sheet? And show you how you proceed. You can use the chat feature. You can, just say use one or whatever to show you, because I want you to know how to do it. I'll walk you through the theory, how to proceed with calculation, what negative means, what are you looking for to say that the precipitation will take place? How will you figure it out that this is my precipitate? Somebody to pick for me. Somebody say, Amy, say I use barium chloride and sodium sulfate. So let me go back to where it is, barium, sodium sulfate, barium. Oh yeah, this is it. Amy saying that I use that as an example. So, and remember the concentration here on my iPad, this is what I have. This is what I have here. I have, here I have barium 0.20 molar barium chloride. This is barium what? Barium chloride, and it is aqueous. And I also have what? I have sodium sulfate, and look at the chemical formula, NO2 SO4. This is aqueous, and it is 0.20 molar. These are the concentration. And assuming that, both of them will form a precipitate. We will assume, look at what I'm going to do now. Look at what I'm going to do when I mix the two. Or first, before I mix the two, I'll say for barium chloride, barium chloride. This is before I mix. I have chloride ion, negative, not, I don't need that. Not the 2. This is, all right, this is aqueous fast reagent. Plus barium. 2 positive to form barium chloride. Barium chloride. And this is solid. The other has the inverted. Remember, we are looking for precipitation. For precipitation, the equation here should be what? Should be balanced. I should balance out barium from barium chloride here. Sorry about, my stylus is not responding well. My iPad is old. I bought the Apple. It's not working. 5th generation. So remember, it was 0.2 from the direction. So if this barium was 0.2, the concentration for chloride is 0.2. That is before I mix. No, 0.4. Before I mix is 0.4 because I'm multiplying it by 2. I'm multiplying it by 2. This is 0.40. Why am I multiplying it by 2? Because from the balanced equation, it is 2. The concentration for barium is 0.2. We don't have the concentration for solid. We don't have the concentration for solid. The other reagent is sodium sulfate. So for sodium sulfate, that means we have SO4, 2 negative, and this is aqueous, plus Na2, no, not 2, but this is Na alone. This is Na going to Na2 SO4 like that, SO4. This what I'm doing here is finding the concentration of each ion so that when I mix, I'll know what I'm gonna use for my reaction quotient. So it was 0.2. This needs to be balanced out for 2 moles of sodium, NO2. Initially, this was 1:1, so this is concentration of barium, sulfate molar, and the concentration for sodium is 0.2, no, 0.4, no, 0.2. You multiply by 2. So for that confusion, you multiply by 2. So this is 0.40. I need to know the concentration of ions, sodium, barium, chloride, sulfate, because those are the key players in my, precipitation reaction. I should do this so that you see that whatever I have here is before you mix. Before you mix, you need to know the concentration. Let's see when we mix now. When we mix the 2 reagent, understand that now we have mixed the reaction, and it is double replacement reaction that barium, all right, barium, this is from the first reagent, Ba2 positive, and chloride negative, sodium sulfate N2, this is positive 1, and sulfate like that. So this is 2 negative. This is gonna help you in writing the correct formula for. If you look at the cation, barium and sodium are now negatively charged. Chloride and sulfate ion, they will exchange, they will switch. Look at how they will switch. And this one will combine with that. So that when you write fast, you see, it doesn't really matter how you label your possible precipitate. I can say one is barium sulfate. Remember, 2 and 2 will go away. This is solid, that is fast. I didn't mean to do that. Go back. Yeah, this is the first possible precipitate. The second possible, number 2 here, all right, is sodium chloride, NaCl, and use the correct formula. 1 and 1 will go away, and this is another solid, all right, another solid. We do like that. So I've done what? I've done my possible precipitates. 2 forms of solids can possibly be formed. We don't know yet which one will form. Now, for number 1, let's see. For number 1, look at how I've labeled my precipitation, my precipitate. This is number 1, this is number 2. We need to calculate this term right here, delta G, or let me write here, delta G node formation of barium sulfate, We need to do that for solid number 1. Using the equation, all right, delta G node formation is given by the formation delta G product, and there is M there for coefficient in the balanced equation, minus N delta G node, superscript, by the way, it's superscript, delta G node reagent. If this is being formed from the solid, see from here, let's see, barium, this is going to combine with that. You assume that a solid is being formed, from barium, and this has to do with the sulfate ion. Remember, we have mixed now the solution. In order for this to form, barium and sulfate should combine, 2 positive, so that is positive 2, and it is aqueous going to it, barium sulfate, and this is solid. Now we're going to use the table. All right, there is a table here. Let's see if I have it here. Is this right here? No, yeah, this table right here. You see this? That's why we are given here product minus reagent. This one, you look, this is the product right here. This is our product. This is our reagents. If I plug in this equation, I will look at the intersection between barium. Is this, where is barium? No. There is a complete table. Maybe I didn't get that. There is a complete barium, and this was just an example. Let's see if I had that. I think I had a complete this one, is it right here? No, not this one. Barium, yes, it's the same thing. Sorry, it's the same thing. If you look at barium and sulfate, you see where sulfate is forming? Barium, where they intersect this point right here. Barium ion and sulfate ion, this is the standard free Gibbs energy formation of barium sulfate. So my product, using the equation up there, will be product will be 13. Somebody to help us with the equation. And somebody with a calculator, this is 13. And the coefficient is 1 to 1 to 1 to 1. So we don't need to worry about anything. 13, 62, point what? Point 20, point 20. What I have here is my product. If I add something else like coefficient of 2, and then I'm gonna multiply by 2. Reagent, all right. This is how you take care of the reagent. Look at what I have in parentheses, big bracket. My reactant is barium ion and sulfate ion. You have to look for barium right here. This is the value I have, and this is minus, in parentheses, minus what? 560. 560.77. All right, plus. For sulfate ion, this is by itself. This is by itself. Negative 744, point what? 0.53, 0.53. And that is my product. So let me pack up again. For barium sulfate, you got to see where the ion intersect to form the solid. It's right there. This is the product. And then for individual ions, you got to look at where the ions are, So if it was silver, it's going to look at that. If it was iron, it's going to be like that. If it was calcium, it's just going to be like that. If it's chloride, iodide, you just have to look for individual ions. Anything right here is for the formation of, say, barium iodide, the intersection right there. Barium nitrate, the intersection right there. Barium sulfate, where they intersect. Sodium iodide, that's where they intersect. That's how you use to find that. Let's see. For what I have here, this will be positive. So if I have 560, 0.77 plus 744.5, 3, and I have negative 13, that will be right here. Let's see, this will be now, this will be, let me go back, what was that again? 1362.20. This is 1362.20 minus 13 or 13 or 5.30. This is just gonna be 1362.20 plus 13 or 1305.30. And what is the value? There is a minus here. There was a minus there. There was a minus there. This will be what? 1362.20 minus 1305.30, and I get a negative 56 point what? 90 kilojoules. This is kilojoules. So I know if I was doing my data sheet, for my number 1, I had labeled my number 1 here as barium sulfate. I have delta G node for my barium sulfate, which was my number 1. How I labeled. For number 2, all right, which is sodium what? It was sodium. If you look at sodium chloride, sodium chloride. Let me just fast forward. Delta G naught for number 2, which is sodium chloride. We still use the same thing, product minus reagent, product minus reagent. Here is sodium, okay, aqueous plus chloride, aqueous, going to NaCl2, not Cl2, it's just L, solid. Remember what we had when we cross over? Sodium here will cancel, it's just 1 to 1, 1 to 1. So the equation is what we have in here. Using our table here, all right, I see product, sodium chloride, sodium and then chloride. It is negative, product minus reagent. Using this equation, delta G node formation will be summation of delta G node product minus delta G node. This is delta G node summation of delta G node product, no reagent. Product negative 384.14 minus, if we look at for sodium, it is negative 261.99. So this is negative 261.91 plus. For chloride, it is negative what? Negative 131.23. Everything in there. So I'm just gonna add the 2 and see how it goes. 261.91 plus 131.23. From what I get, and I see it is 393. So 393, this will be minus 384.14 plus 393.14. So this will be minus, it's just gonna be minus 384.14. And I have 9, positive 9. Kilojoules. So you fill in on the data sheet, the possible formation for sodium or second salt. So you have now what? You have now the values for salt 1, salt 2 for delta. We need this. We need this term so as to find the delta G node for non-standard state, And remember, for this non-standard state, we use the equation. Let's go back all the way. It's right here. Look at the iPad right here, the little screen right here. To get this term right here, this one, use this equation. You already find this. That's why you have to do for each salt. Standard change in free or change in standard free keeps energy formation for each possible precipitate. Up to this point, we don't know which one is, will precipitate out at non-standard state. So I'll use this equation right here. To find which one is the precipitate. And for barium, all right, for barium sulfate, which was my fossil, what I'll do is just do the using the equation, and I have the values for each one of them. This is negative 56. So if I have 56 in a 90, I'm just gonna plug it in there. LNO, so this is what we'll need to use. This is what we'll need to use for delta G RXN. For the fossil is given by delta G naught, all right, plus, this is formation, this is at standard state, plus RT ln of what? ln of Q, ln of Q. Now, this was negative 56, negative 56 point what? 0.90, 90, and this is in kilojoules, plus in parentheses 8.314, this is in joules, by the way, times 298, can use 298 times ln of Q. ln of Q, or Q first of all, Q is given by product, concentration of the product. It is given by concentration of the product over concentration of the reagents. Remember, so number one was barium what? Barium sulfate, barium sulfate. We'll go back to, once we mix barium and sulfate, remember the concentration will be, I have the original concentration. I drew a line before we mix. The concentration of barium is 0.2. The concentration of sulfate is 0.2. So each one of them will be 0.1. Once you mix, it will be a half of what you had. So here, it will be 1 because it is forming a solid. Remember, concentration of solids are unity, so it's gonna be 0.1 times 0.1, 0.1, 0.1, 0.1. So I have that as 0.1, 0.1. Reciprocal of that is 100, 100. So here time is ln of what? ln of 100, ln of 100. What is ln of 100? ln of answer? It is 4 point. All right. This is the same as, I can cancel that and say times 4.6 0.05, 605. So ln of 100, all right, natural log of that. So I can use that. Let me erase here so that I can have some space. So I know now the natural log of 100. And when I plug in the equation, 8.14 times 298.15 times 4.65, that is in joules, so I divide by 1,000 to change to kilojoules. And I have 11, so here is minus minus 56.90 kilojoules, all right, plus 11.176. So I'm just gonna say minus 56.90 and I end up with negative 45.72 kilojoules. So I have this for salt number 1. That is salt number 1. And I'm going to write it down here where it's correspond to whatever you have. Remember, when you assign it as number 1, it's going to correspond to number 1. Whatever correspond number 2. Let's look at number 2. So number 2 was sodium, what? Sodium number 2 here. Sodium chloride. And delta G for that is non-standard state. Delta G known for non-standard state. Let me write it nicely. Is given by delta G naught formation, that is at standard state, plus RT, and remember this is Kelvin 298, we use room temperature, ln of what? ln of Q, reaction quotient. From this calculation for sodium chloride, this is what we found. Positive what? Positive 9. So this is positive 9 kilojoules plus 8.314 joules times 298. Now 15 times ln of Q. Let's find first of all Q. Q is given by the concentration of products, of concentration of reagent. Remember, it's precipitation reaction. We are assuming that this is a solid. We are using this equation right here, that it is going to form solid right here, sodium chloride. So it's product over reagent. In the concentration of these ions, concentration of these two ions, when you mix will be half the original before you mix. Before we mix that, let's see, before we mix that, what was the concentration of chloride? What was the concentration of sodium? Before you mix, what was the concentration of chloride? What was the concentration of bromide? This is before, and this is before, and that's why I had drawn that. You got to do that so that you know when do you use or when do you change the concentration to something else. When you mix the two, the concentration will be half the original. This was my original concentration. So my original concentration. All right, and this will be 0.2. So each one of them will be 0.2. All right, if you want to 0.2, that's the original. And from the balanced equation, it's just 1 to 1. And from 1 to 1, we only say that it is 1 over 0.2. All right, times 0.2. 0.2 because the original concentration was 0.4 and 0.4. This coefficient of 2 here does not play any role because precipitation is a function of the ion, which is 1 to 1. If it was something else, and then we will now use that 2 or whatever. If you look at the background, the one we use, it's based on when you write the precipitation equation, is when you introduce a square or, but since it is 1 to 1, it will just be the value you have here, 0.2 and 0.2. So instead of doing that, it's 0.2 times 0.2, that's what I have. Reciprocal of that, 25. So ln of 25, natural log of 25, I see it is 3. So instead of what I have here, I will use 3.2121. And with that, we are now in a position to determine the delta, the enthalpy or free keeps energy at non-standard state. Times 2 times 298.15, that is the temperature. So I'm doing right now, times the gas constant, 8.314, 8.314. So 8.3 times that. So what I get here is 7,979.01 divided by 1,000 to change to kilojoules. All right, divided by 1,000 kilojoules. I get 7 point, so positive 9 here. This is positive 9.00 kilojoules minus or plus. All right, 7.979 kilojoules. I add 7.9 to original plus 7.979, and I have 16 positive 979 kilojoules. And remember what we said at the beginning of the lecture or lab, that positive means non-spontaneous. After this calculation, I know the free keeps energy at non-standard state for my possible precipitate number 2. It is possible. For precipitate number 1, it is a negative 45. So when I mix the two, my chemical formula here, precipitate formula, will be barium sulfate, So that's what I want. In some cases, you'll end up with positive. That means there's no precipitation reaction. You have to write no precipitate or NR. If you end up with negative, you have to step back and retrace your calculation. That's what you will proceed, and you'll do the same thing for all the reaction. All right, that's what you need to do in all the reaction. I expect you to once you figure it out, which equation, it's gonna be easier for you to show calculation. Please attach any additional papers when you submit your work. I don't want to see only chemical formulas here, chemical formulas, and I don't see any calculation on how you are at. You saw how I was able to label it. Even though I know which equation to use for this, I didn't just plug in the numbers here. I want you to write neatly, that whoever doesn't know anything will understand that the values here came from here. I did the same thing, even though, rewriting the same thing, okay, somebody will understand that, oh, you had labeled possible precipitate number 2 as sodium chloride. And by the way, I think I made a mistake here. Just been a long day, excuse me. So this will just be sodium chloride. No subscript 2. And you write it down, you plug it in the equations, it's just say make a conclusion on which one is your precipitate, Any question on this lab? It's just like a dry lab. It involves a lot of calculation. Any question? Yes, because it is possible, the precipitate is Danielle. You're right. Danielle Fisher, you're right. Because delta G at non-standard state for barium sulfate is negative, this is the formula for the precipitate. Absolutely, that's right. Our sodium chloride here will not precipitate. We know sodium chloride is soluble in H2O. So there is no way when you have chloride, which you already dissolved, will spontaneously form sodium chloride. No, it's not going to happen like that. So that's how you will answer. Somebody say 56, maybe I made a mistake. Let's see, negative 56. Oh, negative 56, maybe it's, I made a mistake somewhere. That was maybe delta, no.
That was for like the first calculation we did a while ago.
For this one right here, let me highlight that. For this one right here, right? Look at the, you know, you are doing this, right? Look at what I'm highlighting on the
yes, but yeah, that's what that was for.
Okay, thank you. Yeah, I thought you're saying sodium sulfate. Thank you, appreciate it. That's what we need to find the first term, and then we plug it in the equation, and then we produce. I thought you are saying negative 56 is for the entire, you know, calculation for non-standard state here, So that's what you need to do. And if there is no question, that's all what you need to do. The challenge is splitting into respective ions. Sometimes you need to use a coefficient. Sometimes it is 1-to-1 that you don't need to do anything. If I look at the first one, the reaction here is 1-to-1 to 1-to-1. So please look at the background again on when you multiply by 2, when you don't multiply by 2. You split it into 2 fast. Before you, especially when you will be doing this ln of q, you got to split it fast, draw a parallel. Look at this while I draw a parallel. I say, okay, this is reagent 1. What is the concentration of each ion? And make sure the equation is balanced so that you will balance by 2. Otherwise, if I don't have 2 here, I will end up using 0.2, which was given. Yes, if it's small ratio is 1-to-1, I don't need to multiply by 2. Make sure the equation is balanced. And the line here is before you mix the 2 solutions. When you mix now, the concentration will be 1/2 of whatever you add before mixing. And then you plug it in the natural or ln of reaction quotient. Is there any question? If there is no question, all right. If there is no question, I'm gonna stop sharing my screen. And I want to thank everyone for showing up tonight. It is, you know, we have to make the best out of this situation. We're almost getting there. Just work on the calculation to make the experience as seamless as possible and not to create a bottleneck of things to turn in towards the end of the semester. I will also make this, the quiz for this experiment available by weekend so that you are, you should be able to complete it by the other Sunday, not this coming Sunday, but the other Sunday before we meet for the, I think the last experiment, before we meet for the last experiment. It's second to last, and everything is available, okay? Try as much as possible to do the post-lab, the pre-lab, and just submit on the respective folders. If you need to, I can share the, I'm recording this, though I apologize, I didn't start the record at the beginning, but I do have the recording of the entire lecture. If you want, I can share the lecture via YouTube. Just in case you want to go back again, I can share. Let me even make that. Yes, all right, thank you, I appreciate it. Danielle, I'll just post that for everybody. Be on the lookout. I will share the link on Canvas, the same folder, all right? The same folder as, you know, the lab, not the pre-lab, not the post-lab. For the lab, just go back. I'll send out an email again for whoever is not here so that you can go back and, you know, play back. Hopefully you will be able to play back again, rewind and see how, you know, how things are done. And I expect you to, you know, complete the calculation, please get in touch with your lab partners and work together on the way forward with the calculation. With that, I'd like to end the conference by saying thank you, have a good night, wash your hand and be safe, practice distancing. All right, thank you, have a good night.